Advanced Math Lesson 29, the unit circle, very large and very small fractions, and quadrantal angles. All right, so the unit circle we've actually already been talking about for a while, or at least we should have been. And really quick, this is the unit circle right here. Okay, so the unit circle just shows us different instances of common degrees around a circle, like 30, 45, 60, 90, 120, 135, 50, 80, pretty much increments of 30 and increments of 45, all the way around to 360. And we check the cosine and sine of each of them. Cosine being related to the x value of the endpoint of the angle, and sine being related to the y value of the endpoint of the angle. So we have this unit circle going around 360 degrees. And by using our two reference triangles, or our two special triangles, the 30, 60, 90, and the 45, 45, 90, we can figure out the cosine and sine of each of these points, right? And the cosine being the x point, the sine being the y point. And, you know, actually, we don't talk about radian measure yet. So for now, ignore all these pi measurements right here. That's called radian measure. We're not going to worry about that. We're focusing on the degrees, the cosine, and the sine values. So to understand the unit circle, we really have to understand first what sine, cosine, and tangent are. So really quick, if you had me in Algebra 2 or Algebra 1, you know I talk about ratios a lot, because ratios are a really big deal. And if you haven't realized it yet, sine, cosine, and tangent are all ratios. If we say something like the sine of 65 degrees, we're actually wanting to find the ratio of that right triangle. So sine, cosine, and tangent are only used in right triangles. So in this instance, sine is 65 degrees. We're picturing a right triangle with a 65-degree angle. And the ratio that we're looking for goes with our SOHCAHTOA rhyme. All right, so this rhyme actually tells us what the ratio is. So sine is the ratio of the opposite to the hypotenuse. So the opposite side being here to the hypotenuse. So these right triangles are going to give a specific ratio, no matter how big or small, for the 65-degree angle. So what we're saying is, let me see here. What we're saying is when we take our calculator and we type in sine of 65 degrees, I end up getting 0.91, round to the hundredths. Sine of 65 equals 0.91. Okay, that's actually the ratio of the opposite side to the hypotenuse. If I were to turn that into a fraction, that gives me 91 over 100. Let's see, can that be reduced? I don't think so. Yeah, 91 is kind of prime, and 100 isn't going to work. Yeah, okay. So then we get the fraction 91 over 100. Off of a rough estimate, that means I can draw a right triangle with a hypotenuse of 100 and a leg of 91, and this angle will be almost exactly 65 degrees, and let's prove that. So let's go ahead and call this angle theta. If we go with a length of 91 and a hypotenuse of 100, sine of theta should equal 91 divided by 100, right? Okay, so let's take 91 divided by 100. Punch that into our calculator. And we're allowed a little bit of our margin of error, so we get 0.91, right? That should have seen that coming. So I'm putting in a margin of error for it, and we should get something close to 65. So if we take sine negative 1 of 0.91, we should come out with the angle of 65. So if we do the inverse operation on our calculator, oops, I get 65.5. Right? And I think that's a pretty fair margin of error since I only use the hundredths place. So that's how the ratio works. If you were to take two sides of a triangle and divide them, you can always get the exact same angle. Again, remember this 0.91 came because I rounded. And it's going to be the same. So all three of these are ratios. And ratios are the reason why this works, is because this circle with a radius of 1 creates the exact same triangle here as it does here. So you'll have the exact same ratios, even though the degrees are different as we go around the triangle. They'll all be in increments of 30, 45, or 60. So that's the first half. Now, next we're going to talk about the quadrantal angles. The quadrantal, hold on, let's see here. Quadrantal, quadrantal. We're talking about these four angles, all right? The corners, or the separation of the quadrants. So quadrantal angles would be 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Or 0/360 degrees, I guess is the better way to say it. And you'll notice as you go up the unit circle, if we started at 0 and we were moving up, we'd use a triangle to solve this one, a triangle to solve this one, a triangle to solve this one, and then you get to 90 degrees and you can't draw a triangle anymore. But you do have x and y coordinates. So if the radius of this circle is 1, what are the x and y coordinates of this spot right here? Well, the x would be 0, so the cosine is 0. The y is positive 1, because you're rising positive 1 off of a graph. So that's how we figure out quadrantal angles. We don't actually use triangles, because at each quadrantal angle, you cannot create a triangle, but using the unit circle, you do have an x and y coordinate. And we know from this that the x coordinate is equal to the cosine and the y coordinate is equal to the sine. So if we keep going around, we'll be making triangles, and then we'll get here and there won't be a triangle anymore. It'll be a straight line, and the cosine will be -1, and the sine will be 0. And the tangent, oh, that's important, the tangent, since it's opposite over the adjacent, or sine over cosine, let me see here. At 90 degrees, 1 over 0 is going to give us a tangent of 0. Or actually, is going to be undefined, right? So tangent will be undefined because we can't divide by 0. Now, if we go over here, 0 over -1, well, that's 0. We go down here, -1 over 0, undefined. Go over here, 0 over 1 is 0. So tangents will be 0 and 0, undefined, undefined. Okay? That's quadrantal angles. Last thing we have to figure out, and honestly, learning these is probably easier if you memorize them. There's another good way to memorize it, which is in this quadrant, you can use the all students take calculus rhyme. In this quadrant, they're all positive. In this quadrant, only sine is positive, so cosine would be negative. In this quadrant, tangent is positive, so both cosine and sine would be negative here. All right. And then in this quadrant, only cosine is positive, so cosine would be positive here. Make sense? I hope so. Okay. Last thing we're going to talk about, very large, very small fractions. So to do that, I'm going to draw a graph. What makes a fraction big? What makes a fraction small? Well, we're going to talk about the lengths of numerators and denominators. So they give us a couple examples. Example A is 0.008 over 4. And then we've got 0.00008 over 4. We got to figure out which one's bigger, right? That can be kind of hard to figure out because fractions are difficult. Or let's go with the inverse. The other two examples would be 4 over 0.008. And then 4 over 0.000008, right? Which one's bigger? Okay, so we'll notice in these two cases, in these top cases, the bottom number or the denominator is fixed. The denominator does not change. So as the numerator changes, what happens to the fraction? Excuse me. And then in the bottom version, we have the denominator changing with the numerator not changing. So let's see how that affects the fraction. We're going to do this by graphing two functions. We're going to sketch the graph of f of, we'll say 3 over x. Or should we do 4? Yeah, we'll do 4 over x. Yeah, it'll be consistent. So we'll do the function of 4 over x. And then we'll also do the function of x over 4. And we'll see what happens to the graph. So at 4 over x, Let's try 4, 0, negative 4. See what happens to the graph. If I plug in positive 4, 4 divided by 4 would be 1. Okay. If I plug in 0, can we divide 4 by 0? No, undefined. So that's going to be a hole. Now, let's plug in negative 4. Well, we get negative 1. Okay, so we don't really know what's happening. Let's try 1 and negative 1. So if I plug in 1, I get 4. If I plug in negative 1, I get negative 4. Okay, so let's start graphing some of this. If we go 4 on x and then 4 on y, or negative 4 on y, we get negative 1, and then here we get positive 1. Okay, at 0, we're not sure. At 1, I'm at positive 4. At negative 1, I'm at negative 4. Okay. This is kind of weird. I'm not sure what's going on here. There's kind of like a box. Okay, so let's try 2 and negative 2. So we'll go 2, negative 2. If I put in 2, I get 2. So, and then if I put, oh, sorry, that was negative 2. And then if I put in negative 2, I get negative 2. Okay, so we're starting to see a trend here. What happens if I put it really, really, really close to negative 0? So we'll keep going with x and y. And I'm going to put like, I'm going to put 1/4. What if x is 1/4? Well, if we have 4 over 1/4, that inverts, and then 4 times 4 becomes 16. If we do negative 1/4, we end up getting negative 16. Okay, so if I'm at, let's say this is 1. If I'm at less than negative 1/4, I'm at all the way up here at like negative 16. And if I'm at positive 1/4, I'm like all the way up here at like positive 16. All right, so this graph is moving really badly. Now, let's say, I'll tell you, if we went this direction, we would get even closer and closer to 0. So what the graph ends up looking like is this. Okay, so what this tells us is that as the denominator gets bigger and bigger and bigger, the number gets closer and closer and closer to 0. As the denominator gets smaller and smaller and smaller and smaller, the number gets closer and closer to infinity. And likewise on the negative scale, the smaller the negative, the closer it gets to negative infinity. The higher the negative number, the closer it gets to 0 again. So, the bigger your denominator, the smaller the number. The smaller your denominator, the bigger the number. All right? Oh, wow, this video's gone on for 13 minutes. Okay. Well, to show you the opposite of g of x, it kind of does something a little bit different. The higher, or the bigger the number we put here, the higher it goes. So it kind of does an opposite thing. So as the numbers get bigger, the graph gets higher, and as the numbers get smaller, the graph gets lower. So it kind of does more of one of these curves. And then as a negative, it would look like that. So it looks a lot like a tangent curve. Didn't mean to go on for 13 minutes. Hopefully this helps you conceptually, and I'll see you guys in class.